Hey everyone, welcome. If you're the kind of person who loves breaking down incredibly complex ideas and just getting straight to the core of how things actually work, well, you are absolutely in the right place. Today, we're walking through a fascinating explainer based on Dr. Choi's highly rigorous academic takedown of quantum computing. For decades now, quantum computing has been heralded as this ultimate frontier of technology, the next big leap. But what if the very foundations of this field are actually built on an epistemological illusion? Dr. Choi has put forward a really detailed critique of both the physical and the philosophical underpinnings of quantum technology, and we're going to visually deconstruct his exact arguments today. So get ready to look at the future of engineering in a completely different light.
Okay, let's dive right into this. Here is our roadmap for today. We're covering 5 key areas. First, the crossroads of determinism and probability. Second, the paradox of superposition and measurement. Third, the illusion of post hoc confirmation bias. Then, mathematical fiction exposed by thermodynamics. And finally, a return to real science.
Let's start with Section 1, the crossroads of determinism and probability.
To really understand this, we need to take a quick trip back to the early 1980s, where we saw two radically different visions for the future of computing emerge. On one side, we had the von Neumann architecture. Now, this is the rock-solid foundation of the entire personal computing revolution. It's entirely deterministic, it relies on real numbers and strict causality, meaning every single input and output corresponds to a rigorous physical reality. It's dependable. But then, on the other side, during that exact same era, we have Richard Feynman. Feynman was a brilliant mind, right? His Nobel Prize and Manhattan Project credentials gave immense weight to his ideas. And he proposed a hypothetical, probabilistic model, the quantum computer, which was designed to mimic the wave functions of the microscopic world. But here is the kicker. Dr. Choi argues that Feynman's immense authority effectively granted a massive academic free pass to what was essentially a highly abstract mathematical hypothesis, and that sparked a 45-year academic pursuit that fundamentally diverged from the strict causality of classical computing.
That takes us to Section 2, the paradox of superposition and measurement.
The entire mathematical appeal of a quantum computer basically rests on this simple but massive expression, 2 to the power of n. In a theoretical mathematical realm called Hilbert space, a quantum bit or qubit can exist in a state of superposition. According to the theory, this allows a system to hold in process 2 to the power of n states all at the exact same time. Honestly, it sounds incredible, doesn't it? It promises this parallel processing power that scales exponentially. It's the ultimate dream of having infinite virtual space for computation. But as Dr. Choi points out, computation isn't just about what happens in a theoretical vacuum. It's about what you can actually get out of the machine in the real world.
So the crucial point in this theoretical system is what's called the wave function collapse. You see, in computer engineering, the final, absolutely non-negotiable step of any calculation is measurement. You have to read the data out as a classical bit. But when you measure that quantum system, that massive virtual space of 2 to the power of n states instantly collapses. It shrinks all the way down to a single, solitary 0 or 1. Dr. Choi highlights this as a fundamental information theory contradiction. You have this theoretically infinite internal workspace, but your physical output bandwidth is fundamentally restricted to a single bit. Think about it. If you have to run the exact same operation millions of times just to statistically verify an output, you aren't actually experiencing exponential speedup. You're just waiting on random statistical convergence. It is a massive data bottleneck, and it destroys the practical utility of superposition.
Moving right along to Section 3, the illusion of post hoc confirmation bias. Here, Dr. Choi rigorously breaks down the deeply flawed methodology behind these so-called quantum supremacy experiments we hear so much about. Look at this step-by-step process. In reality, because quantum states are incredibly fragile, step 1 is that the quantum device basically outputs a massive amount of random thermal noise. It's largely just chaotic data. So how on earth do they get a result? Well, step 2. A classical standard computer actually calculates the correct answer template beforehand. Then, step 3, the researchers retroactively filter that chaotic quantum noise, carefully sifting through the thermal fluctuations just to find the data points that match the classical computer's pre-calculated template.
I absolutely love this analogy from Dr. Choi regarding this process. He states, it is structurally identical to a primitive rain dance. Perform the ritual until it rains, then retrofit the results. It hits the nail on the head. This perfectly encapsulates the concept of post hoc confirmation bias. because without the classical computer already holding the answer key, the output from the quantum computer is just entirely unverifiable garbage data. Claiming this system is an independent, superior computing device is, according to Dr. Choi's critique, a deep scientific and methodological error. You are essentially generating noise and then retroactively reverse engineering a success story out of it.
Which leads us to Section 4, Mathematical Fiction Exposed by Thermodynamics. And this brilliantly illustrates the core issue with things like Shor's algorithm. In mathematical theory, physicists use imaginary numbers on a chalkboard to show that the probability amplitudes of the wrong answers perfectly cancel each other out, leaving a neat, clean zero. Sounds great on paper, but in physical reality, the actual macroscopic world we live in, negative mass or physical imaginary numbers simply do not exist. You can't just magically erase energy. According to the unbreakable second law of thermodynamics, when those waves cancel in reality, that energy has to go somewhere. It doesn't just become zero, it becomes heat. It becomes thermodynamic entropy. Dr. Choi argues that confusing mathematical symmetry on a chalkboard with actual physical reality is a fatal flaw in the field.
Furthermore, forcing those quantum waves to cancel out exactly how you want them to requires injecting highly precise phase control templates into the quantum circuit. Now, doing that requires an immense external system of classical controllers. The time, the energy, and the computational overhead required for a classical system to calculate and inject these precise mathematical structures completely and totally erases any theoretical nanosecond speed advantage that the quantum chip might have gained. In the end, the classical machine is doing all the heavy lifting just to force the mathematical structure onto the quantum device.
Finally, we reach Section 5, a return to real science.
Dr. Choi's conclusion here is a stark wake-up call for the scientific community. He outlines that we have effectively spent 45 years chasing a mathematical illusion. We're pouring astronomical amounts of energy into cooling these fragile systems down to absolute zero, and the entire field relies on the future promise of a completely hypothetical technology called error correction, just to function at a basic level. Engineering at its core is fundamentally about creating value within the strict limits of physical laws and real-world resources. Dr. Choi urges that it is time to drop the imaginary physics and complex numbers and return to strict, error-free engineering based on real numbers and deterministic architecture.
Which leaves us with this final, incredibly provocative question to ponder today. If a classical computer must always calculate the exact answers beforehand just to verify if the quantum output is correct, is the quantum machine truly an independent computing device, or is it simply an incredibly expensive, highly fragile mirror reflecting the classical computer's own work? It is a profound question that challenges decades of technological hype, and it completely reframes how we should view the future of computation. Keep questioning, keep learning, and thank you so much for joining me in breaking down this fascinating explainer today.